Welcome to the GOB laboratory at Mercy University. Today we're going to be taking a look at the density of a metal cylinder and trying to determine the specific gravity of a urine sample. In part A of this experiment, we're going to use a graduated cylinder along with an analytical balance to determine the density of a metal sample, and then we're going to compare it to the true value to determine our percent error. Here's an overview of some of the materials and pieces of equipment that we're going to make use of in this experiment. To weigh our metal sample, the first thing that we do is tare our balance to 0. Then we place the metal sample inside the analytical balance and close the door to make sure that air currents don't affect our reading. We now let the reading stabilize and then make sure we record that on our data sheet. It looks like our value has stabilized at 27.1727. We want to make sure we record that on our data sheet with all significant figures that are displayed, and for us on the analytical balance that's going to be 4 decimal places. Next, we want to fill our graduated cylinder with about 4 milliliters of water. The exact amount is not important, but we're going to look at the bottom of the meniscus and read off the exact value. So take a minute, pause the video, and see if you can read off what value is displayed on the graduated cylinder. Remember that each small marking corresponds to 0.1 ml. You should have read off a value of around 3.97 or 3.98. It looks like the meniscus is just below the 4 milliliter mark. Now we want to add our metal sample to our graduated cylinder, being careful not to splash out any water. You can tilt the graduated cylinder at an angle and slowly slide it in so that we don't lose any water in the process. You can see now that the water level has risen, and what we need to do is again read the bottom of the meniscus and record the final volume of the water in our graduated cylinder. Take a minute, pause the video, and see if you can read off the value on the graduated cylinder. Make sure that you record the final volume on your data sheet. You should have come up with a value of around 7 milliliters, since it looks like the bottom of the meniscus is right at the 7 milliliter mark. Now we're ready to begin our calculations. The first thing you want to do is calculate the change in volume due to adding the metal sample to your water. So you're going to take the final volume minus the initial volume. Now we're ready to calculate the density of our metal sample by taking the mass of our metal sample divided by the change in volume, which represents the volume of our metal. Now let's compare our calculated density to the densities of other metals at 20 degrees Celsius to see if we can determine the identity of our metal. Once you've determined the identity of your metal and its corresponding accepted or true density, we can compute our percent error relative to that true value. Remember that percent error is calculated by taking your experimental value minus the true or accepted value divided by the true or accepted value times 100. In all cases, make sure that you're carrying through the correct number of significant figures throughout your calculation. In part B of this experiment, we're going to be making use of a volumetric pipette as well as an analytical balance to determine the specific gravity of a urine sample. First, select a urine sample and be sure to record the sample ID of your urine sample. To begin, place your flask on the analytical balance and tare the balance to eliminate the mass of the flask. This is because we're only interested in weighing the urine that we put in the flask. Once we've zeroed the reading, remove the flask from the balance, and now we can add our first urine sample to the flask. You're going to use a volumetric pipette, and here you use the pipette pump by rotating the wheel to draw the fluid up into the volumetric pipette. You'll notice that the bulb fills, and we'll draw the liquid up to the calibration line. The bottom of the meniscus should be just touching the line. Make sure that you hold the pipette vertically when reading it, and dispense by pushing in the release lever on the pipette pump. Let the pipette gravity drain and don't try to blow out the tip. You want to make sure that when you do this procedure, you're not doing it inside the analytical balance. You don't want to get any fluid on the analytical balance because it could damage it. So make sure that your flask is outside the balance when you're adding liquid to your flask. Once we've transferred 10 milliliters of urine to our flask, we need to reweigh it in order to get the mass of the urine. Place the flask on the analytical balance and wait for the reading to stabilize. Here it looks like the reading is 10.1347 grams. Make sure you record that in your data table. The volumetric pipette if used properly, dispenses a volume of 10.00 milliliters. To continue our procedure, we need to re-tare our flask so that the reading is back to 0 and it's ready for another sample of urine. Remove your sample from the analytical balance once you've tared it and begin to pipette a second sample. Again, you're going to draw up the liquid in the volumetric pipette to the calibration line so that the bottom of the meniscus lines up with the calibration line. While keeping the pipette vertical, transfer the liquid to your flask and let it drain under gravity until it's completely empty. You're now ready to reweigh your flask to take the mass of the urine that you just added. Place the flask in the analytical balance and close the door, and let the reading stabilize. Here it looks like our mass is settled at 10.1634 grams. We're going to record that in our data sheet, and again we're going to record the volume of our volumetric pipette, the liquid that was dispensed, which is 10.00 milliliters. Re-tare the balance to begin a third trial. This will make sure that your reading is zeroed for your next urine sample. Remove the flask from the balance and proceed to pipette another sample. You may find that holding the base of the pipette with your other hand helps keep it steadier as you're trying to pipette out of the sample bottle and into your flask. The key to getting good results in this lab is just good repeatability. Make sure that when you draw the liquid up in your volumetric pipette that you try to line up the bottom of the meniscus with the calibration mark every time. And if you're looking at that calibration line at eye level, that will make sure that you get it just right. Another tip for good results is to resist the urge to blow out the tip. So don't try to use the wheel on the pipette pump to force the liquid out faster. Just take a little time, let it drain naturally under gravity, and you'll get the best results. There may be a little bit of liquid left in the tip of the volumetric pipette when you're done. That's okay, that's the way it's calibrated. Once you've transferred the liquid, to complete the third trial, reweigh your beaker to get the mass of the urine that you just pipetted into the flask. Close the door, let the reading stabilize, and then record your result. Here it looks like our final mass is settled around 10.1724 grams. As you complete each trial, you can also calculate the density of the urine by taking the mass of the urine divided by the 10 milliliters that we pipette each time. If your instructor has asked that you complete more than 3 trials for this experiment, continue the next trials in the same way that you've completed the others. Remove the flask from the analytical balance after you've tared it, and then pipette an additional 10 milliliters of urine into your flask and then reweigh it. Again, if you feel unsteady holding the volumetric pipette, you can use a second hand to steady it or the container that you're pipetting into. It's always good practice to hold onto the container so that you don't accidentally tip it over with the pipette. Weigh your urine sample by placing your flask back on the analytical balance, closing the balance door, and then waiting for the reading to stabilize. Here it looks like our value is 10.1619 grams for the fourth trial. We'll go ahead and record that in our data sheet. For a fifth trial, we continue as before. We're going to pipette another 10 milliliters of urine into our tared flask. Now we're ready to reweigh our flask for our fifth trial, so place it back in the analytical balance, close the balance door, and wait for the reading to stabilize. Here it looks like our mass has settled at 10.1683 grams. We're going to record that now in our data table. Make sure that you complete the calculation for the density of urine for each of the trials that you've completed today. Next, we're going to record the temperature of our urine sample. To do this, we're going to make use of a Vernier LabQuest 2. You plug the temperature probe into the end of the LabQuest, and it should come up with a temperature reading in degrees Celsius. All we have to do is insert our stainless steel temperature probe into our urine sample, and we'll give it a few seconds for the reading to stabilize. Here it looks like the temperature has settled around 20.4 degrees Celsius. We're going to go ahead and record that in our data table. Using the temperature we just measured, we need to look up the density of water at that particular temperature. In this experiment, our temperature was 20.4 degrees Celsius, so I'm going to go down to the row labeled 20 and go across until I get to the column labeled 0.4. If I find the cell where those intersect, I see that the density of water at 20.4 degrees Celsius is 0.99812 grams per milliliter. If you haven't done so already, make sure that you take the mass and the volume for each urine sample to compute the density of urine for each trial. Now we need to compute the average density of our urine by taking an average across all of our trials. So we just add up the density for each trial and then divide by the number of trials that we did. To compute the average specific gravity of our urine sample, what we need to do is take our average density that we just computed and divide it by the density of water at the temperature we measured. To compute the percent error in your urine specific gravity, your instructor will provide you with the true or accepted value for the specific gravity for your particular urine sample.